Yes.
Because I lost my voice. I lost my voice this month.
For YouTube users also, the mic is.
And you have the
Pointer.
the
Pointer,
pointer.
yes, sir. Just close it. No, no, don't give anything.
And to go back here.
This is my.
It's not a pointer. It's not a laser pointer.
Yeah.
A
Can
laser.
you enable laser pointer or there is?
Yes, we can enable here laser pointer. So otherwise, we can use the local one. But the
But
local.
the local one will not have a transit from.
Yes, sir.
So why would this enable?
No, I would prefer.
Yeah, laser pointer. Right.
Yeah.
There is a setting for it. We just have to enable.
But the people who are on Zoom, they will not be able to see the laser pointer. That is one thing. So what is the problem with this pointer?
He is more used to that. He
Oh.
is binding it into whether it is there or not.
It's a PDF.
It has.
Sir, when it has a valid point, sir,
Okay.
if you use a laser pointer locally, the people on Zoom will not know what you are pointing. So with this, everybody will know what you are
I
saying.
understand.
Yeah.
Okay. Okay.
Right.
Makes sense. But people on, yes, people on Zoom, they
Yeah,
don't,
They will not.
it's not, I mean, it's
Yeah,
not,
this screen is not visible. They see this shared screen.
yes, they don't see me. No,
They do see you. Yes, sir.
yeah, they're
On
very,
this image,
very
yeah.
small.
No, but they will change the camera so that you will be on a focus when you start speaking on it.
Okay. But when I'll be in the focus, but not,
Yeah, they will not.
okay. Anyway, it would not help.
Yes.
It sound, I think I prefer to be here than
You
to
can
be
sit
behind.
here and Ashish will introduce and then he will welcome
No,
you.
but not during the talk.
During the talk, either way, whichever way you're comfortable. If you feel the right side or left side, whichever is your comfortable side.
I think I prefer to be here.
Yeah, whether you want to be on the left of it or right of it also, it's up to you.
Yeah, keep it.
It's up to you.
We'll wait 1 minute.
Yeah.
Hello everyone and welcome to this special edition of our research Télécom. And we are here to hear Professor Sakarovitch to give us a nice talking and request to introduce it.
Welcome everyone. So it's a pleasure to have Professor Jacques Sakarovitch among us today as the speaker. So Jacques is an emeritus researcher at CNRS and also an emeritus professor at Télécom Paris. So his main research interests are in the area of theoretical computer science, in particular automated theory. He has worked on various aspects of automated theory, in particular like word combinatorics as well as algebraic aspects of it. And he's also the author of this book, Elements of Automated Theory, which was published by Cambridge University Press. Previously, Jacques has been a director of Federation of Computer Science Laboratories in Universities of Paris 6 and Paris 7. He has also been a technical chair of the Working Group on Foundations of Computer Science at IFIP, International Federation of Information Processing, where he is currently serving as the vice president. Today, he is going to talk about his work on formal language theory, which has also implications on number theoretic problems, I think. Yeah, so thanks, Jacques. So
Yeah.
all yours.
Well, thank you very much. It's a great honor and a great pleasure to talk here. I mean, great honor. I'm not a Nobel Prize nor a Fields Medalist, but you accepted you offered me to talk. It's very kind. And it's a great pleasure to be here at the IFR, which is a marvelous research institute, really. So I'm very grateful to Shibashis to have invited me so I had a very good condition here to work with him and to give some lectures to his student and him. So, and this talk is, I mean, somehow kind of a secret garden or side project I have. So it's a subject where mathematics and several subjects of mathematics, such as number theory and theory of and symbolic dynamics, and theory of infinite roots meets with some aspect of theoretical computer science, such as automata theory, transducers, and combinatoric of words. I will try to, sketch a few results we had on it, and more important, to give you the feeling of, there are many problems, I think fascinating problems, and I hope that you will be at least fascinated, or maybe you can enjoy it. So this is based on, it's, I've been working on the subject in the last, let's say, 25 years. But eventually we get some result, which allowed us to publish at least. So first result in 2008 with my colleague, Christian Fournier, with whom I was working on automata theory and transducer for some time, and Shigeki Akiyama, who is a number theorist in Japan. And then later on, I had a student, a PhD student, Victor Marceau, with whom we made some progress also on some other aspect, but which probably I won't have time to present. So I will begin with what could or should be the end, but it's very convenient to begin by the end. So you're sure that you will have enough time to, otherwise. And this is the problem in number theory in which we made a small progress, as you can see. And afterwards, I will spend some time to explain you what is the relationship between automata theory and the writing of number representations, where there are a number of things. And then we'll get back to, this will explain the first result. And finally, I'd like to present something very fascinating, a property, but I have no good name for it, so I don't name it yet. And if time allows, but which is unlikely, I will show you another aspect of all this thing where order generates chaos or disorder. So what is this problem by Mahler? Kurt Mahler, not Gustav Mahler. So let's start we start from a number, theta. Okay. And suppose that if theta, and you are interested in the fractional part of all multiples of theta. Okay, this is a very simple problem, so that you can, okay, if theta is rational, then the fractional part of all multiples of theta, that is all the n theta for all n in n, this is a finite set. Whereas if theta is irrational, it's easy to see that it's uniformly distributed. That is, if you take any interval on between 0 and 1, okay, belonging to 0 and 1, then the number in the limit, the number of times you will hit that interval with this fractional part will be proportional to the measure of the interval. Okay, so this is something that you can do with, let's say, high school student. Okay, it's very obvious. So the problem I'm interested in is somehow the same kind of question, but instead of considering the multiples of the number theta, I'm interested in the fractional part of the powers. Okay. Of course, this is obvious, there is no interest if theta is smaller than 1, because theta will decrease and theta to the n will tend to 0. So that's not the point. So the question is, what if theta is bigger than 1? And we are interested only in the fractional part. Of course, if theta is an integer, it's not interesting. But so now there are powerful, let's say, results in analysis that for almost all theta, this sequence of between 0 and 1 is uniformly distributed. But the problem with this statement for almost all, when you specify one element, you have no idea of what the answer will be. Okay, so it tells you something, of course. I do not say it's not interesting to know that, but somehow, at the same time, it tells you nothing. Okay, so of course, okay, we have a first point. So for a certain family of numbers that number theorists like, they call Piso number, right? That is, in one Piso number, okay, you know what Piso number are. It's an algebraic number. It's an algebraic integer that is the root of a polynomial with integer coefficient where the leading coefficient is 1, okay? And it's a Piso number if its modulus is greater than 1 and all its conjugate, the modulus of all its conjugate is smaller than 1, okay? It's a very special class of algebraic integers, and somehow they behave like integers, okay? So they behave like integer, and so they behave like integer in the sense that this integral part, this fractional part will tend to 0, so that 0 is the only limit point, and so there is no point. Of course, it's not uniformly distributed. Now, for other things, for other number, we don't know. And the first thing we can do is to make experiment, compute. And what one sees, it looks uniformly distributed for transcendental theta, like pi, for instance, or E, and very chaotic for rational numbers. Okay. And the only result we have so far is that if theta is rational, okay, this set fractional part blah, blah, has infinitely many limit points. But this is very far from saying something on the distribution. But so I didn't know, but people working in number theory, these kind of problems are really very difficult. I've met once Hillel Furstenberg, and I was presenting what I'd done and said, oh, this is very difficult. These are very difficult problems. So I stopped until I met Shigeki Akiyama. So I'm sorry.
Is it rational or can be extended to all the way to algebraic numbers over
No, this is for rational. For algebraic, I don't know. Even. It could.
Square root.
Hmm?
Square root.
No. No clue. It may be the case that it should be better than rational, less chaotic, but I have no answer. Somehow, there is one kind of algebraic number for which, okay, the answer is no. For other algebraic numbers, I don't know. I don't know, and I think nobody knows. Okay, so in that situation, one possibility is to make another problem, to make a new problem, trying to get some information. So this is what Mahler did. So you fix one rational number, P over Q. Okay. And now you look for every number psi, real number. Okay. You look at the distribution of the fractional part of the power of that rational multiplied by that number. Okay. So it's another problem. There is a problem.
I just noticed that there was something in the meeting room. I don't know if.
So that will take place.
Okay. So for the same reason, for the same theorem as before, for almost all psi, this set is uniformly distributed. Okay? But once again, it doesn't tell. It's for almost all psi, but we don't know. For a given psi, what is the situation? So now, so Mahler stated that problem. He defined this this sequence, that is M of psi, M of psi, and then he proposed two problems. That is, given an interval or a subset, which indeed will be finite union of intervals. He is interested of determining the set of numbers psi such that this sequence MPQ of psi is eventually in the set I. Okay, and so there are, from this point of view, there are two, let's say, kind of research. I mean, either you hunt for I which is as large as possible so that this set ZPQ of I is empty. So it would be, it's not possible. So it would be, let's say, something that indicates that maybe you're going to something which is approaching uniform distributivity, because something which negate uniform distributivity is not true. And the other side is you're looking for I as small as possible, such that this set is non-empty, which is, on the contrary, proving that there is something which is not uniform. Okay. So just to give you an idea, too, and Mahler showed that the set for the rational number 3/2, 3/2 of the set of the interval 0, 1/2, he proved that it is at most countable. Everyone is convinced that it is empty. Okay. Okay, so we are far from a satisfactory answer. Okay. But it's still open. Everyone is convinced that it's empty, but yeah, I mean, if it were not empty, okay, this would prove that for certain psi, this sequence would be really not uniformly distributed because, or eventually they will be all in the first half. You will maybe better understand. Yes. Yes, MPK is eventually containing I. Okay. Okay, so this is, so the search for big I with MT, well, somehow the best thing is known that it is empty if you have an interval which is of length 1 over p, which is not big. Okay, 1 over p. Then any interval, and so the first in 95, these people showed that the set where you can put an interval where this is of length 1 over p will be empty is dense, and Bugeaud showed that it has the full Lebesgue measure. And I remember I discussed with Bugeaud, is really upset that he could not, he is sure that it's true for all integer, but he can show only that it is of full Lebesgue measure. Okay. That is with probability 1, you take NES and then, okay, and it will be empty if you have an integer, an interval of length 1 over p. So I would like to go a bit further. And now on the contrary, so the Pollington showed that if you take this interval between 4/65 until 61/55, so it's a centered interval of length 57 over 65. This is non-empty, and there exists at least one psi such that the sequence M blah blah is eventually in that restricted interval. Okay, and our result is that now we take two.
Eventually contained there, I'm not understanding something. That means that it's not uniform, it is not contained, it enters it. No.
So because a certain sequence is eventually contained in
It means that there exists an n such that for every n larger than n, this that number will
which means that it will not be uniformly distributed.
No, sir. No, contain means that it eventually does it visit the interval frequently often, or does it visit the interval always?
Always.
So it never goes out of it, but then it's not uniformly distributed.
Yeah.
So that's a counterexample.
It's not well, it's a counterexample. Now it's not for if you could say Xi, there exists a Xi. If you could say Xi equals 1, it would be a counterexample to. If you could say Xi equals 1, now you know that there exists a Xi, but the original question of the
modified question was for inside, not this one. That modified question, this is a counter, this is a counter. That's what I meant.
okay. So the example there again. Okay, you look at this Xi such that this sequence is eventually contained, so that is this sequence is not uniformly distributed. Okay. Okay. Okay, and so what we did, and then we showed that there exists that for every P over Q, P bigger, larger than or equal to 2Q minus 1. For instance, 3/2. Good, and I will speak of 3/2 essentially. Meets this condition. There exists a subset which is a union of Q, in fact, intervals of length 1 over P. So the total length will be Q over P, such that this set there exists a infinite number of psi such that the sequence is eventually contained in that. Okay. So, and for 3/2, 2/3 is smaller than 54/65. Okay. So, okay, so you have to be, I mean, I'm not a number theorist, but Shigeki Akiyama always he was happy with that. So if he's happy, I'm happy. Okay, so, and in fact, we can characterize those psi. It's a characterization. I cannot, it's not exactly, can you tell this number? Okay. Okay, so the set of psi such that this sequence is not fall into this subset is exactly the number of psi which have 2 P over Q extension. Okay. What does that mean? This is somehow the first topic, but I'm afraid it will be the topic of this talk. Okay? Okay. And now I will try to go a bit faster and speaking on the representation of numbers. Okay. So we agree, I suppose, that number exists. For instance, this figure tells you about the number pi over 4, which is just a ratio between the perimeter of the circle and the square. And also it's the same thing as the ratio between the surface of the disk and the surface of the square. Okay, so number exists, but if you want to compute with them, you have to write them. And now the question is how we write numbers. So I will take the example of first of the integer base, and I take 3 as a base. Okay, so what is the writing of an integer? It's a word, okay, over the alphabet 0, 1, 2. And if I take any word of such a word, so this word is the representation of the number, which is in fact the sum of the power of 3 multiplied by these digits. Okay? And so the language of all representation is all words, let's say, that do not begin with a 0, usually. And a way, and this is the list. It's no surprise. And I prefer to represent these words on these 3. And I start from the state 0. And I follow a path, and along the path, I read letters. Okay, this is a labeled graph. Okay, and if I read a path, for instance, 2, 0, and I reach a node which is labeled 6, and all integers are written that way. And I can make if I want to get rid of this constraint of not beginning with a 0, I can allow 0 also at the beginning. And the consequence will be I will have my full ternary 3 as representation. In fact, it's even better. Okay. Or even I can, if I want, I can write it like that. There is a small loop over 0, and it will, so the path will be exactly the same as the full tree. Okay? And now, if I'm given a number, I don't say how it is given, but suppose it's given, I can compute this representation with an algorithm, which I call it the greedy algorithm. This is the one you certainly know. You first choose the largest power of 3, which is smaller than n, but n is smaller than the further power, and blah blah blah, and you compute, and you know how to compute the representation of n. This is a greedy algorithm. But in fact, there is another algorithm, maybe you're not aware of it, that you can, instead of choosing the largest power of 3, which will give you the leading digit for the representation of n, you can just compute the smallest, the last digit of n, which will be, in fact, the remainder of the division by 3 of your number. You subtract it, and you have the quotient, and you do it is the same. So you have another algorithm that computes the representation of an integer. Okay, this is the division algorithm, which a computer scientist will tell you, oh, this is a Horner scheme, but not giving the name, but it's okay. Okay, now if we go to the real, we have still the greedy algorithm, as usual. And we know that it's somewhat difficult to apply the division algorithm because we should go to the infinity on the right. And, well, just Woody Allen says, well, infinity, it's very far, especially toward the end, okay? Okay, so we have only this greedy algorithm for the real numbers, okay? Okay, so there is no point to spend too much time on it. And now the same tree, we see that, in fact, it's very convenient to represent all writing of real numbers between 0 and 1. Okay? Okay, and for instance, okay, so the representation of 16/7/27 is 0.121, and 1/4 will have an infinite but periodic, or ultimately any rational will have a periodic representation. Okay, so this is very well known, common knowledge. Okay, so, and now there is a relation between this writing of number and finite automata, and one of the relation is, given I say it's Blaise Pascal, but in fact, I'm a bit cheating because Blaise Pascal, and even though he built a computing machine, he really didn't know what a finite automaton is. But if you read, probably not in Latin, but in its translation, either in English, in French, or in Hindi, or this paper of Blaise Pascal in 1650, then you can recognize almost a finite automaton. And the idea is the following. A finite automaton is a label-directed graph. Okay. Now, in my case, it's labeled by the digit I'm using 0, 1, 2. I'm in base 3. And this automaton, okay, you have a set of states which is distinguished, and it's the initial states. And you have also final states. And now you have paths that are successful if it begins in an initial state and ends in a final state. And now the language that is accepted by this automaton is a set of words that are labels of successful paths. Okay. And this automaton shows you the writing in base 3 of all numbers that are divisible by 4. Okay, it's very, very easy to check. In fact, if you take any writing you start in the initial state, and if you follow the path, so you will end in a state that would give you what is the remainder of the division by 4. Okay, so there is another way to use finite automata in the writing, is the addition. Okay, this is an addition in base 3, and it's probably the way you would teach it to your kids. Okay, you have 0 plus 1 is 1, 1 plus 2 is 10, because 3 is 10. So you write 0 and you put 1 carry, and now the carry 1 plus 1 plus 1 is again 0, blah, 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 and so on and so forth. Okay. It's not the way I would do it as a computer scientist. It's much more efficient. First, you add and you get new digits, larger digits. Okay. This first operation is very simple because you can even do in parallel as long as your word. Okay. And so now you get a new word, a word which is written on the new alphabet. 0, 1, 2, 3, 4. Okay. And what you need is a function that takes any word on that new alphabet, 0 to 4, to the canonical alphabet, 0, 1, 2. And this is realized by a kind of finite automaton, but with output. That is, every transition is labeled not by a digit, but by pair of digits. One digit which is input, one digit which is output. And this, we call it transducer, and this transducer will read your word from right to left. Okay. From right to left. And he reads on the top, and he outputs the bottom, and you get the same result. Okay. So it's very efficient. And in fact, there are, in some computers, this is really implemented. Not exactly like that, but almost. Okay, so it's well known that now if you take any alphabet of integers, of digits, even with negative digits, which I represent with -1. Okay. The normalization that is giving a word which has the same value on the canonical alphabet. This is realized by letter-to-letter sequential right transducer. So right transducer means you read the number from right to left. Sequential means, now if you look at the input, only on the input, you have something which is deterministic. And letter-to-letter means that every time you read a digit, you output a digit. What may happen that at certain final state, you output some digit. Okay. Okay. Now, let's consider another family. So this was the writing of numbers, integers and reals, with an integer base. Now let's consider that, well, we could take a non-integer at the base. So this is what is called by people doing this kind of thing, beta numeration. So beta will be the base. Okay, so we take any real number larger than 1, and we do the same process. We try to do the same process as what we did with integers. So now the canonical alphabet will be 0, 1 until, well, I take this formula, that is, in fact, the integral value of beta. But if I want the formula being valid for integers, I take the integer which is larger than beta -1. Okay, because for integer, it's -1. Okay, and so you have let's say, in fact, integers will not have better representation than any number. So we are interested in any number, and it's not, in fact, we can restrict ourselves to the integer between 0 and 1. And we have the greedy algorithm, which is exactly the greedy algorithm that we had before. In the same thing, it's written differently. So we take a number, we multiply by the base beta, and we take the integral part. And the remainder is the fractional part. And the process goes again. And this is the way we have a representation of the real x in the base beta. And now okay, it is a representation that's proved by Parry. I mean, it's not difficult. And what is remarkable is in the first theorem, due to Parry, I don't remember, it's in, I suppose, in the 60s or something like that. That if beta is piezo, then the set of representation is a rational set of infinite words. So we can also define rational set of infinite words. It's for, you have finite automata and you read your word infinitely, and the accepting condition is slightly different, but it's not important for us. So it's interesting that a notion which is purely defined purely in a mathematical way, piezo, you retrieve it with this definition of rational set. But in fact, the connection, it's much stronger, and that the base beta is piezo if and only if the normalization, the thing I've described for the writing of number in integer base. So beta is piezo if and only if that normalization is realized by a finite automaton. So really, it was a completely unexpected connection between, let's say, finite automata theory and purely mathematical notion. So in this case, of course, you see I write letter to letter finite transducer. It's not sequential. It's more general and complicated. Okay, and now I get to the point of, now what can we do with rational base? In a rational base, if I treat, so I can treat, okay, 3/2, for instance, I will use the example of 3/2. 3/2 is a number I can consider beta number. So I can, but it's not a piezo number. Okay. So I can use the greedy algorithm. I mean, this will give me nothing. I mean, nothing. This will give me representation, but this representation have absolutely no properties. So at least nobody know any property of them. Okay. So the idea is to consider another representation in something which is nevertheless the base 3/2. So I change the alphabet, I add a 2, and in fact, what should I do? Okay. And the base is divided by all element of the base, that is the power of the base divided by 1/2. In fact, it is as if I had the digits 0, 1/2 and 1 to be. It's, and now what I do, I use almost the division algorithm that I used in base 3, but I modify it because I multiply at every step by, if I have P over Q, I multiply by Q. So this division algorithm, of course, ends, give me a result, and it is a representation of n in this base 3 half. Okay. Okay, I have exactly the same kind of Horner scheme. And it's not difficult to see that with this algorithm, for every integer is given a unique representation. Unique finite representation. Okay, and so we denote, well, this is the representation in base 3 half of n. And now the question is, what is the set of words that I get in this way? Okay. So this is the list of the first writing of number. Beside the fact it all begins with 2, 1, it's not clear that there is any property. In fact, there are a lot of properties that do not appear immediately. Now, if I write it as a tree like that, this is the tree I get. Okay, so this tree plays exactly the same role as the tree that I've shown you for in base 3. The difference is it is completely, I mean, it's not as regular as the ternary tree was, and I must say that in fact it is completely irregular. Okay. So it has all the property with respect to the representation of numbers. So the path will label the, you can put the number in the radix order of your tree, and now any path, the label of the path will give you the representation of the number of the integer, which label your node, and everything is okay, it's fine. The difference is now every distinct subtree every subtree of this infinite tree are distinct. So this is, from a point of view, 3 is very, 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 not rare, but I mean, very irregular. Okay, so for instance, people know that if you represent regular languages that way, that you will be a finite number of distinct subtree, infinite subtree. So now you have every subtree is different. Okay, so this is the tree. But there is something that still remains from what we had, and it will be very important. Second, in that the normalization somehow, or the digit, if I start from any set of digits, I have a letter-to-letter sequential right transition, which will transform my word on this alphabet of digit D star into a word over 0, 1, 2. This automaton will not recognize whether this is the writing of an integer, because this is impossible. The set of integer is not rational. Okay, but it will give you something which has the same value in this base 3 half. Now we can try to represent reals in that base. So this is again what was the representation for in base 3, and I remember we were using the greedy algorithm. For the base 3 half, we have a problem because the greedy algorithm will give us nothing, And the division algorithm for real is not possible. Okay. So we do exactly the contrary. We decide that by definition, the tree of the representation of the real will be the tree that we have built with the representation of integers. We have seen that in the case for 3, the representation of 3 is exactly, in base 3, the representation of integer is exactly the same tree as the representation of the reals that are computed with the greedy algorithm. So now we do not compute the representation of real from the real. We say, okay, this is the tree of representation of reals. And so that is, we take the infinite paths in the tree we had. Oh, I'm sorry, this is still the case of base 3. So I show you that this is the case of base 3. So every real has at least one expansion, at most 2. You know, the 2 is 2 is the same thing at 1, 0, 0, or 2, 0, 0. And the set of real which have 2 expansions is infinite. Now, for the representation of reals, so we start from our tree. We expand it before, and this will be a representation of real. But you see, the difficulty is that the representation goes one below the other. So this makes it difficult to compute them. But nevertheless, this is mathematically well defined. This will give you representation of reals. I mean, you have some work to do, it's compact, blah, 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 but everything works well. So this is a way of defining representation of real. And as we have seen, so there is a maximal word. Okay, here this is the maximal, which represents a certain number omega. We have no idea what this omega is. I suspect or conjecture that there is no, in fact, there is no formula, I mean, closed formula, like log 3 over log 2 or something like that for that number. It's a constant, I would say, like the Gauss constant, but okay, it's a constant, but I don't think that there is you can compute from other functions. It's really, it comes from this representation. Okay, it contains the maximal, and otherwise, okay, every real has at least one 3/2 expansion. So it can be given, which means that. And the set of real that have more than one expansion, they are exactly, oh, I'm sorry. Okay, okay, these numbers that are, you go inside until the infinity. This is a number between 2 infinite words like that. So this will have 2 representations. And of course, you have one such number corresponding to every integer. So it's countable. And no element is eventually periodic. And I mean, the prefixes are not expansion. And so every real at most 2 3/2 expansion. Okay, so in the last 5 minutes, I can reach. So somehow this is the trick we have found. Now we have there is a mathematical way of computing a 3/2 representation, not the expansion, but representation of number, and it is given by this formula. For any z, you compute this value, okay? H of z is 2 times the integral part of 3/2 of z minus 3 times the integral part of z. This is a function, it's periodic of period 2, and this is the graph on 0, 2, okay? And you see that this function takes 4 values, -1, 0, 1, 2, okay? And now from that function, we can compute a sequence of digits in that new alphabet that will represent the word any number. Okay, so I said there is no way of computing. I'm sorry. There's no way of computing the 3/2 expansion of a real, but there is a way of computing a 3/2 representation, but on a larger alphabet. Okay. And here comes, okay, and so we remark that if at a certain point, so if the kth digit is 0, then the fractional part of this quantity belongs to 0, 1/3, and if this digit is 1, it's really this pointer, it's not easy to, it is 1, then the fractional part of this number is between 2/3 and 1. And so we have seen that going from one alphabet of digit to the canonical alphabet of digit is realized by a finite transducer. Left, right, sequential transducer. Okay, in fact, it's a very simple one with 2 states. And this is true as soon as P over Q, as P is large, greater than or equal to 2Q minus 1. So with 3/2, we are in the good case. Okay, so this is it. And now, since we have on one hand the C, which is a representation, if we take the expansion of the same number, then this will be the pair of these 2 infinite words will be the label of an infinite path of in this transducer. Okay. Now, if we have 2 distinct expansion, there will be 2 distinct infinite paths in the there will be 2 infinite paths in the transducer, 2 distinct. If there is 2 distinct infinite paths in the transducer, it will be in the square of the transducer, it will be an infinite path that goes out of the diagonal. Because if you stay in the diagonal, it's the same computation in the 2. So, and now we see that if we go outside of the diagonal, we have to stay, because if we are an infinite path, we have to stay. And what we have, the input should be 0 and 1. Okay. So which means that if we have 2 distinct expansions, then this companion representation of the number should eventually end with 0 and 1s only. And if it ends with 0 and 1s only, then it means that the fractional power of the 3 half to the n multiplied by that number is either in 0 1/3, either on 2/3 1. So these numbers which have two distinct expansion exactly answer the problem. So I'm sorry, I've been much slower than I expected. I don't know whether it's my voice, but this stop, it's just 1 hour. I stop. Or if you want, during the question, I can give you this property.
From the larger alphabet to the base that you want. So how many states are needed in the transmission? Is that something that is easy to do?
So you have 3 cases, the integer cases, the beta piezo case, and this rational case. In every case, there is a formula that tells you exactly the number of states. I don't know just by heart, but there is no mystery in it. Okay, it's rather simple one. I should have the answer. I apologize, but no, okay, it's not necessary. It's a number which is not very big. There is no, let's say, combinatorial explosion. Something is exponential. Or it's linear. There's no dramatic things happen. It's just a simple computation. Okay, give me 2 minutes. I want to show you this. Okay, 2 minutes. Okay. This is again the tree, but it's written differently. But it's the same tree, 3-half tree. And now I'm interested in the minimal words. Okay, a minimal word so I start from any node, and I follow every time the smallest possible. So the label will be either 0 or 1. Okay, so I can look at everywhere. So every integer has a minimal word attached to it. Okay. All these words are distinct. It is conjectured, strongly conjectured, that these words are, they're random. That is, the density of 0 and 1s both exist and are equal to 1/2. We are far from being able to prove it. But now the question I asked is, what is the relations between these minimal words? The reason of this question is because if you take two distinct rational, you will get 2 distinct trees, and you will get 2 distinct family of minimal words. Somehow my claim is these 2 family of distinct words, of minimal words, are different. So, but you have to have some criterion to say, okay, that there is a family, they must have something in common. So I have a conjecture that a way to saying that they are not so different is that there exists a finite transducer that take one to the other. Okay. So this would mean that somehow there is kind of infinite information which is contained in one infinite word, and that this infinite information is just transformed by a finite machine into all these different words. Okay. This is my conjecture. But of course, we are far from having proved it. But okay, it's true, but this is stupid. But now, here comes kind of lapin du chapeau, just rabbit out of the hat. So I take this tree. Okay. Now I invent or compute a rule for transforming every label digit into pair of digits. Okay. It's not so complicated, and I can give a simple rule for any rational number corresponding. Okay. So I transform my tree into a transducer with a very simple rule. Okay, now that transducer transforms every minimal word into the next one. This is completely magic. I mean, it's not, once you know, I mean, it's not difficult. I mean, it's not a difficult property. What is, I find completely amazing that I start from the same tree, the tree that represents the number. I have a simple rule to transform the digit into pair of digits. And this gives me a transducer. Okay, it's not a finite transducer. It does not answer the same question. But it shows that there is something, it's not auto-similarity, but there is something in the tree, in that set of representation that contain this way of representing, going from one minimal word to the other. Well, this is true for the case when P equals exactly 2Q minus 1. But there is a result of the same kind, I mean, in the same kind, in the other case. Sometimes you have to add some transition, a very simple way. Sometimes you have to delay some transition. But so somehow this tree contains other things than just the representation. And this is, I find, magic, and I wanted to show. I thank you. I apologize for these three supplementary.
I will just take a minute to give him a memento for this lecture. This is a 40 years of asset colloquium which we have finished. So this is.
Thank you very much.
Thank you for giving us a enlightenment. Very nice talk like this.
Thank you. Thank you very
I
much.
request everybody to join for the tea and discussion. So you can put it.
Oh, thank you. Thank you very much.